Again, welcome to the lab. Today is November 16th. There will be, of course, no class next week because of the holiday. And so we still have this lab, which really covers two labs, as I mentioned in the lecture earlier. The two labs are the AC circuit and the RL, basically time constant. Technically, usually we add to it also the LC constant, the LC not constant, the LC time characteristic, which is omega naught really, the period which is 2 pi times square root of LC. In a typical lab, we can do that because of the fact that there is no such an ideal situation where you don't have a resistor in it. So usually you have a resistor in the mixed, and that's why you can't really do that in the actual lab. So you jump right straight out to the RLC circuit. And that's exactly what we're doing today too. So we have two labs. The one that introduces basically the time varying phenomenon, and also since we measured we did the RC lab where we measured the time constant for the resistor and the capacitor in series. The same thing we're going to do today. We're going to take again the inductor and the resistor, and we put them in series and basically find the time characteristic, which turned out to be square root of, there is no square root. It's going to be L over R. Okay, that's what tau in this case is going to turn out to be. So we're going to do that, and then also we're going to jump into the same thing that I was discussing earlier, which is the discussion for today's actually topic, namely the behavior of an RLC circuit in terms of two kinds of major behaviors. There is a transient, which does not stay too long, and it decays exponentially no matter what situation you're in. Whether you have the situation where R over 2L squared is bigger than 1 over square root of LC, or I'm sorry, bigger than 1 over LC in this case, since I squared the other term. Or situation where will all the case, of course, if does this sound better now?
It sounds good right now.
Yeah, I think the problem was I was connecting to a different internet. I was using actually the phone for some reason. Okay. And the phone I was using oh man, it was a mess. I just realized that. So right now the internet should be fine. I'm sorry, okay? So anyway, so again, we have like the example of the leaf. So if your example, you basically, you excite it, you blow on it, or there is a wind just that comes in, so it's going to oscillate, but then ultimately it's going to stop, because a leaf, for example, on a tree is just like an RLC circuit in this situation, like a mass on a spring system. Same thing, for example, if you take a mass spring, you attach to a damping, in this case usually viscosity, and you excite it, namely you move the mass out of its equilibrium, what happened in this situation is going to oscillate, but because of the damping, it's going to stop at some point. Okay, if the damping is too big, then what happened in this case, the mass, you pull it out, but then it's going to be brought again, damped right away. So that is actually the system where there is too much excitation in it, okay? I mean, too much damping in it. Or you could be in a critical situation. In all three situations, the mass will come to a stop. Okay. In your car, for example, if you have good shock absorbers, the car goes through an oscillation, but immediately they cancel it. Okay, you don't really have oscillations. If you have oscillation, you have bad suspension system that you need to take it to the mechanic and have it fixed. So this is a transient. All of this behavior is the example of transient. In the case of the RLC circuit, for example, I could build a charge in the capacitor and then have no other source of energy other than the charge in the capacitor. I have a resistor and I have an inductor. So the L and C, they try to oscillate with one another. Basically, there is an exchange of energy, but between them, there is that resistor that is constantly basically draining energy from the system. So it's going to dissipate energy at the end and you're done with it. So it's not good, okay? So that is an example of a transient behavior. Okay, transient behavior actually is not a desirable thing. It can be very, very dangerous. It can actually kill you because the intensity is so high. For example, when you plug in the current in your household, I don't know if you noticed that, but sometimes there is a spark that comes out of the plug. Okay, or when you unplug it too, there is a transient that's going to go through that. So there is actually a spark through it too. Usually in a circuit, you don't want the transient. Transient is really not a desirable thing. You want to get rid of it as much as possible. That's why you have protection, for example, on the system to protect it from high voltages, high currents, because those things usually they're associated with transient. The steady state, though, is the one that deals with the applied current. Then in this case, for example, the wind is blowing constantly. So the leaf at that point, initially, for example, it has its own frequency, so it's going to oscillate and something, but then after that, it's going to follow what the wind does for it. Or you take the leaf, for example, and you blow on it, but constantly, with a constant blow, with the same, basically, breath. So what happened in this case, the leaf initially is displaced out of its own equilibrium, and initially probably it's going to try to oscillate, but oscillate around the new position. And then it's going to stay in that position oscillating until it damps and stays there. Same thing, if you take a mass and spring system, for example, with damping and it's too still, but instead of putting it this way, put it in the gravity. So the spring will stretch first and then oscillate around the new position. And if there is no external position, external excitation is going to stay stretched because of gravity, okay? So that is what I mean by steady state. Now, the spring normally has this length, but when you put it vertically, it's going to stretch because of the mass attached to it. So the additional amount is the steady state. So that is really what I want you guys. I want you to come up with different examples for steady state versus transient behavior. Okay, before we delve into the lab. Do you guys understand the task? So we have a system at equilibrium, and you disturb it from its equilibrium. If it's disturbed, like for example the mass, you take it out and you push it this way. So in this case, it's going to oscillate and come back to its equilibrium. Okay, no matter how much damping there is. Too much damping is going to come right away. Too little damping is going to oscillate and come back still. Okay, as long as there is damping, always there is damping in this situation. If you put it backward, then the situation is going to stretch first and oscillate over the new location and damp around the new location. And then the spring at the end will stay stretched by that amount. And the same example holds true for anything, for buildings, for anything like that, including electrical circuits, by the way. Okay? If you guys take DFQ, differential equations class in mathematics, this has actually big implications because you will have differential equation of the second order, similar to what we did for the RLC circuit. As a matter of fact, your teacher will give you this example from the RLC circuit. It's the easiest one to start with, even though they don't teach you electricity, but they assume that somehow you're familiar with this expression, with the equation that we wrote earlier today in the class. Okay, they give you that. Okay, if they don't give you that, they give you the mass spring system, basically mass spring and damping system. It's one of the other two. Okay, they don't usually give more complicated examples in the beginning than this. Okay, and then they prove actually in calculus that the general solution to a differential equation, in this case, non-harmonic differential equation, because it has an excitation on the other side, is this combination or the sum over the steady state, okay, which is the solution with the term on the other side, so-called non-homogeneous solution, plus a transient, which is a homogeneous solution with no external side on the other side. Again, I want you to watch out for this thing if you're ever going to take DFQ. If you don't take DFQ because you're measuring on something else, well, that's probably the most extent you're going to get out of it, which is fine, I think, for the purpose of what we're doing for this lab. Does this make sense to you guys, the task at hand? You're going to illustrate examples of transient, let me write them down. Transient, oh man, transient and steady state. Yes? Okay, this one person is confirming. So let me get into the lab. First of all, I need to download the stuff because I think I know where they are, more or less. Hold on. Okay, so the lab form. Since I have it open, let me go back into your stuff in here and share with you the PDF file. I can just open it. Okay, show more stuff. So many things open, I have to really be careful into looking into it. Okay, so let's try it one more time. Share. Here, found it. Okay, so this is the lab instruction. Remember that file that you guys had from before? You really need that file too for this purpose of the lab because you're going to do stuff with it too, okay? The one that has to do with the JavaScript, not JavaScript, the Java, okay? So you need to have that Java file for you guys. If not, it's actually part of the lab instructions anyway. You need to download it for this lab. Okay, does everybody know what I'm talking about? I can give you actually the name of the file. Let me go into the lab instructions. It's the Circuit Construction Kit ACEN for English .jar, okay, which is a Java file. Yes? No, there was no discussion in the first one for us for the question. I deferred it to the lab, and this is the question of the day today, is to come up with examples of transient and steady state, okay? I need you to make a distinction between the two, because when we do the resonance later on in chapter 31, that will actually come with a lot of implications in it, because we will focus mainly on the steady state, but actually never forget that there is a transient in the solution. In order to satisfy the initial conditions mathematically, you really have to include both of them, and the math is so cumbersome that it becomes ridiculous. Okay, there is a point in here in this lab that I'm going to make about this very same issue too. Mathematically, it's not really hard, but it's too long. You start writing an equation and then it's going to be several pages just to get stuff done with it, which is most of the time meaningless, because you're dealing with that, excuse my French, basically stupid transient. Okay, the transient is really a nasty thing that you have to deal with. Okay, but it's part of the problem. It's always part of the problem. But when we do, most of the time, what we do, we focus only on the steady state, because we assume that we have waited long time, so that whatever transient behavior was, basically it's gone. Okay, so in this case, the focus will be on the steady state. So again, that's basically the question that you have. But my question for you guys is that for that file, okay, I really need you to get into that file. Okay, so what was the okay, so remember we did the RC circuit. So today is going to be the focus also in the RL circuit, and then we're going to do the RLC circuit. Okay, I strongly recommend that you guys read through the details. Do not start on the objective until you complete the whole lab. Basically, then you have an idea of what you're doing. Okay, other than that, I will tell you basically what it is. So again, this instruction is, the picture is slightly different. Okay, we really don't have this kind of power EMF. Okay, we only have a steady state normal battery. Okay, I should have really changed the graph in here. So what we have an RL circuit, basically an inductor and resistor, and they are in series, as you can see. Usually in the lab we have a switch to turn them on. Okay, and basically I have the VR, the voltage across the resistor, and the voltage across the inductor. And I have a steady state, in a sense. I only have basically, I'm not steady state, as I have an EMF battery, E epsilon. So basically it's a fixed charge, it's a fixed voltage. Okay, 12 volt if you like, or 15 volt. So again, if I go back into the analysis we did in lecture, basically the voltage across the inductor plus the voltage across the resistor are equal to the EMF. We just apply Kirchhoff's rule, where the voltage across an inductor in this case is given by this expression. This is a drop in potential, LdI over dt, and drop in potential is I of t. So these two drops must be equal to the voltage across the EMF in this case. Okay, the voltage from this point down to this point is the same as this sum of these two voltages, or the voltage across the EMF. The solution that we found actually together for the current that we did earlier was this expression. Okay, except that in this situation we have an initial current. Okay, in that situation we didn't have an initial current in the circuit. So in here, I think there is an I naught in here. I forgot to put the I naught in here. So I hope that you guys have caught this thing. So this should be I naught. This should be I naught. Okay, in here. That's what makes this expression then correct. Where tau in here is L over R. This is a time characteristic that we're supposed to find. Obviously, the inductor itself is a wire actually, and it has its own resistance. So it has its own resistance. So we have two resistance. Usually it's represented by a pure inductor in series with a resistor, and that is the internal resistor of the inductor. So if we replace that R by the R equivalent, So this will be the R equivalent, this will be the R equivalent, but this will be the voltage across the resistor, the pure resistor, in this case, this R. So if that's the case, I have to multiply by it, and then the expression will look slightly different. This is because in practicality, if we do this lab in the classroom, we will not get this result. Okay, this is not what we will get, because an inductor by itself has its own resistance. So this is closer to the answer. And the reason why we need an I naught, you will see clearly, is that because the starting point for the actual simulation, it does not start with a zero current. It may start with a finite current already running through the circuit. So that's why you need an initial current to account for that. So in other words, the curve at the end will not be exactly linear. I mean, will not be exactly, will not pass through the point 0, 0 in the Cartesian coordinate system. It will be shifted a little bit. It will have a y-intercept, and the y-intercept is because of that initial current. So that's why the expression that we did earlier in the lecture needed to be modified with this one, okay? And you can prove, it's easy, you can prove that this is actually a solution to that equation. All you have to do is take the derivative with respect to time. When you take the derivative with respect to time of this constant, that's 0. When you take the derivative of this times the tau, you will drop, in this case, minus tau. And then you're going to multiply R by this expression and add them and force this 2 to be adding up to epsilon. Okay? From there, you're going to find basically the conditions for the solution. Okay, that's exactly question number 1. Verify that equation 1 is a solution to equation 2. What is it? Oh, this is backward. Verify that equation 2 is a solution to equation 1. Please correct that. That is the second point that you need to mention in your discussion, that you have corrected question 1. Question 1, verify that equation 2 is a solution to equation 1. Because this is, basically check this expression using this one. Does everybody understand the question? Okay, so basically just take the derivative, multiply it by L, and multiply R by I, and check that they are actually, you're getting 0 there, okay? And I want to see the steps that you have done, that you're actually understanding what's going on. So this is a lot simpler than what I did earlier for you guys when we actually found the solution, okay? Question 2. You're going to get this file, okay? It's already part of the download that you have, okay? And make sure that your computer has Java already in it. And then basically, let me open that file. And I hope that you guys are also opening it. And I'm going to share that with you to show you step by step on how you make this thing in here work for you. So let me go into the folder where everything is. I'm going to open this one in here. I'm going to maximize it. I'm going to stop sharing the screen. I'm going to share with you the screen, this one. So this is how it looks like when you guys open it first, okay? The first thing I would recommend to do is change to schematic, okay? And then show advanced. Under show advanced, I want to hide electrons, okay? And then add a wire resistivity, some wire, but don't add too much, okay? Just a little. To simulate how the real situation would look like. I'm going to look into the picture to see how that basically circuit look like. So what I have an EMF, I have also a switch, I have a resistor, and I have an inductor, okay? So let me put this stuff in. So I'm going to take an EMF, in this case, this one. I have a switch. I'm going to take this one. I need the resistor. So here is a resistor. I have to take an inductor. Here is an inductor in my circuit. Okay. And I need a bunch of wire to connect this thing. So I'm going to connect this too. Make sure you drag things and they're connected. Okay. I'm going to connect this wire here. Usually they snap on, okay, in position. Then I'm going to take this wire and connect these two. Make sure you adjust them correctly. I'm going to take another wire in here, connect it in, oops, undo. I can't undo, I have to disconnect, split junction. I split it in the wrong place, okay. And then move back. Come on, move back the whole thing. Make sure you drag things and they're connected, okay, to make sure that you have connections, and you have a connection. So basically, I built the circuit now, okay. I need the voltmeter for my things in here. I'm going to connect the voltmeter to the resistor. I'm going to be measuring VR. For some reason, it's going to go back and forth. I don't know. Let's see here. Okay, so we have the positive on this side, the negative on this side, so it's fine. Okay, this is good. Then I need a timer, stopwatch. Okay, here it is. I'm going to pause this one right away. Your instruction to pause it right away, the play, the animation, and then start it. When you start it while it's paused, it's still reading 0. Okay, so everything looks good. I want to change the value of the EMF because they said it needs to be, how much was it? It needs to be 12 volt. So I'm going to put a 12 volt in here. You can actually select it and type it manually and say done. Okay. Show values to make sure that it persisted. Okay. The inductance is supposed to be how many henries? 50 Henry, and the resistor is 10 ohms. So everything looks good. Okay. I have 10 ohm in here. This is 50 Henry. The only thing I had to do is change this value. And this is basically how the circuit would look like. Then in the instructions, let me get the instructions again. Make sure that you have an R of 10 ohms, the EMF is 12 volt, and the inductance, make sure the animation is stopped before you start the stopwatch. Okay. Then start and stop the animation and record the values of the time and the voltage across the resistor. You need to repeat the previous step to fill all the rows in the table 1, and then you fit the data. Okay, so I'm going to basically what I'm going to do in here, I'm going to start the animation and stop it right away. Oops, sorry. I did forget to do something. Let me reset this one since it's stopped. Okay. The reason why I forgot to close the circuit, okay, if you look at the picture, while you have the animations paused, it's fine. You can start it right now, okay? So we need to close the switch, okay? Otherwise, nothing is going to happen. So we need to close the switch. Now, we should see something. So again, we're going to start and stop. Oh, man. That is no good. So let's open the circuit again. Okay, I forgot to start this guy in here. So now we're in good shape. So we're going to close the circuit, okay, because we need the time. So we're going to start this one and stop it. Right now I have a reading of 1.03 volt at the time of 0.45 seconds. Remember, I have 12 volts in here. So the maximum I'm going to get the voltage in here is 12 volts. So if you see yourself running too high voltage, that means you're in the time too long. So try to stop it right away, okay, when you do this. Because ultimately the voltage will drop to 0 here. It's infinite initially. There is no voltage in here across it. It's open completely. So the voltage actually is this voltage initially. And then it's going to start to decrease in here and increase in there. So at this point, I'm going to go back into my, my table 1. And record the data. Table 1. Let me show you basically what that is. Stop sharing that screen. And come back into this table. And the time is 0.45 seconds. And the voltage across in here is 1.03. How much is it? Yeah, 1.03 volts. 1.03 0.03 volts. Okay. Remember, the EMF is 12, so this number 1 minus something is over 12 is going to be less than 1, so the log is going to be negative in here. Okay. So that is one thing, but it's going to be definitely a finite value. So I'm going to stop this sharing and go back into the animation. Where is it? Here it is. So now I'm going to start it and stop it right away. Pay attention to the voltage. You don't want it too high, okay? You need 10 points. 10 points of data in here. So start it and stop it. Right now, 1.785. The time is 0.81 seconds. And start it and stop it right away. Then the voltage is going to increase. So this is the third data for me. The fourth, the fifth, the sixth, the seventh, the eighth, the 9th, and the 10th. That's plenty, okay? If you're curious trying to find out what happened if you wait a long time, okay, it should go as high as 12 volt in here. That's the maximum voltage you're going to get in here. And this one should be dropped to 0 then. So let's run that quickly in here and see if we wait for a long time, an infinite amount of time actually. So the voltage right now is increasing in the capacitor, in the resistor. That means it's in the inductor is dropping. After a while, it's going to increase very slow. I mean, the time clock will continue to run super fast, but the voltage, you will see it increasing because it's an exponential. Remember, the voltage is actually the current too. So the current at the end, the time is increasing super fast, it's still the same speed, but the voltage is still now increasing. Hardly you're going to notice it. But it's going to reach 12 volt and basically stop from increasing. Right now, you will have to wait for a long time to see actually an increase by thousands of a volt. So this is saturation. That is the exponential growth that you saw. Initially, it's going to increase rapidly. That's why you need to catch it rapidly, okay? Otherwise, you're going to be dealing with the same values, and it looks like you have a constant function. Right now, the time, you'll have to wait a long time, really, okay, for it to reach 12 volt. Okay. Actually, it's not going to reach 12 volt necessarily because we have resistance in the wires too. So there is a drop in voltage everywhere in here. So it's going to reach a little bit less than 12 volt. But that is the bottom line. That's why you have a y-intercept in there. So I'm going to stop the animation in here because we reached, I think, the saturation in here. Does this make sense to you guys, this part of the lab? At least collecting your data.
Yeah, it makes sense.
Okay, very good. So let's continue now with the instructions. So imagine you have done 10 points in here of data. You're going to also calculate the natural log of 1 minus this divided by 12. Okay? So I assume that you can do that either using Excel or you're using your calculator, it doesn't matter. So you're going to find these values and you're going to plot that value as a function of time. So y as a function of time. It should be a linear function. Okay? It should be a linear function. So it's going to be a decaying also function because remember you have an exponential growth in it. Okay? Once you do that, you're going to graph the data, and you graph it either with the enclosed graph or use your own Excel file. I don't care. It doesn't matter, really, as long as you graph it. And then from the graph, you're going to get the y-intercept and the m, the slope, okay? Because you're going to use a linear fit. And the slope is going to be comparable to minus r over L. That is really what we're trying to compare it to. Obviously, you need to see how far you are off from R over L, where R is 10 and L is 50. R is this 10 and L is 50. So the answer should be really minus 1/50th or minus 0.2, or not minus, it's going to be positive in this case because we we're going to take the absolute value in here to compare the two, because the time characteristic should be R over L, but the slope itself is going to be negative, okay, because it's decaying. The point being in here is this should compare to the ratio of these two numbers. How far you're off basically is dictated by, first of all, this error in the wires. You have more R's, and you have actually another R usually typically in here. And if it comes out too wrong, that means the simulation, there is something wrong with the simulation. So again, you're going to answer this question, question 2, based on your graph and based on your data that you collect. So at this point, I think everybody is on board. It should not be hard for you guys. I hope that you guys can get your data and plot it and do things with it. So this is building up a current in an RL circuit. It's basically depends on how R and L are. I mean, I was going to extend how we do it really normally in the lab. What we do, we change the value of R because it's very hard to change the value of L. Usually we have one inductor. We don't mess around too much with it. We change R, L, and we will see that basically the tau, when we're going to plot tau as a function of R, and we will see it's a linear function. But I decided not to do that because this is part of a different lab that I normally do in class, but we're just going to stick to this idea in here. Does this make sense to you guys? This is the first part. The whole portion in here, up to the graph and the data and all of that, before we get into the second part. Okay, so let's get into the second part of the lab, which is the Lrc circuit. So again, we have a source in here. We have a capacitor now. We have an inductor, we have a resistor, and we have a source that is steady state in this case. Again, we're assuming at t equal to 0, there is a current I naught in the circuit, and there is actually a charge Q naught in the capacitor. So this is a little bit more general than the one I did in class earlier. And the EMF is actually epsilon, okay? So the equation is similar, except now you have a capacitor. And the capacitor is Q over C. And the VL is L d second of Q over dt squared. And R, this is similar to what we did in class earlier. So the equation would look like this, basically, that you're supposed to solve. This is called a non-homogeneous because you have epsilon on the other side. Second order because of this derivative in here, second derivative, differential equation, which is ordinary differential equation, which is the easiest, one of the easiest, not the easiest one. It's the second most easiest with differential equation that you're going to have in DFQ. But we're not going to rely on that. We're going to do it our own. This is similar to the substitution I did in class, where we found A and B, A and gamma, and B was deferred to the initial conditions. And the initial conditions are quite complicated in this situation because I have an initial current I naught and I have an initial charge Q naught in the capacitor. Okay? But it's doable. So this is, the math is identical to what I did in class. So you take the derivative of Q because you need it in here, and you take the second derivative because you need it in here, and you sub in equation 3. So this is how it looks like. Again, A over C plus B over this times C. So you take the B exponential as a common factor, and you do this stuff in here. And immediately you equate the constant to the constant, and you force this term to be 0. And the constant equal to the constant gives you A equal to C epsilon, like what we did earlier. Except I used the substitution, the typical substitution, R over L, which is equal to 2B. And 1 over LC equals to omega naught. So I was using a little bit different notations in there than this one, which is the same thing. At the end, we got the same answer. So this is the gamma plus and gamma minus. And as I said in the class, when R over 2L squared is it's bigger than LC, this is going to be a real number. Square root is going to be square root of a positive number, which is real. In either case, these two solutions will be positive because in the case of the positive sign, that's positive no matter what. In the case of the negative sign, it's still positive because this term is in here 2 squared minus something. So this term at the end is going to be less than this one. So when you subtract a small number from a bigger number, it's going to be still positive. So both of them are going to be positive, and the exponential in here will decay because gamma is positive for both cases. If gamma are negative, this is an exponential growth, which will really be weird because where is that energy coming from? It's only coming from a battery. So at the end, if you have no battery, so this energy must go away because of the resistor. So I'm glad that this works this way. So I'm happy in a sense that this works this way because it makes sense. If it did not, then we have a problem. See how we always ask, does it make sense? Things must make sense, okay? So these two terms are positive, whether you take the positive sign or the negative sign, because you cannot have energy from nothing. You cannot somehow basically end up with a system that grows energy over time. So that's not going to be possible. So if that's the case, again, those two solutions are positive. In this, sometimes in the books, you will find that the gamma plus minus is equal to as capital, basically gamma, capital gamma, plus or minus capital lambda, okay? Where both lambda and gamma are positive. Big gamma and big lambda are positive. Now, in the case when r over 2l squared is less than that, so that means this number is negative, and square root of a negative is an imaginary number. So the notation usually in the books, they write it as gamma plus or minus I omega. Both gamma and omega are capital, and both of them are real. So this is a complex number now. This term will always ensure the decay, because again, you will have an exponential of minus in here, times big gamma t. But this term will ensure the oscillation. So again, this will be a decaying oscillation, oscillations that decay. So in the first case, voltage decay is exponential, while in the second case, the voltage decay is exponentially in an oscillatory fashion. There is a third case I didn't mention in here, where both of these two terms will be identical, equal. So that is actually called the critical decay, critical condition, and that is basically also will decay because of this term always will ensure decay. But that has a little bit of a growth, a little bit of a bump, and then it comes down. But that's really usually it's just on the boundary between the two. Okay. Okay, we found tau for the RC circuit to be just R times C. We just found tau from the previous lab to be L over R for the RL circuit. Now you're supposed to take this expression and you invert it for gamma plus, and you invert it for gamma minus to find the tau plus and the tau minus, because this expression is gamma times t. So we can write t over tau. In order for that way to define by time characteristic, the time characteristic has to be 1 over gamma. So you're supposed to take these expressions with the plus and the minus, and you invert them, and you can express them in terms of the taus. So tau plus, with this positive solution, will have tau RC over 2. And you can clearly see it from here, okay? It's R over 2L, L over R, but then when you do the ratios, the L over 2, the 2 will become in the denominator in here. And the same thing, you're going to find it in here. So it's really an algebraic expression in here, playing with the algebra. So you take the positive sign, you invert it, and you multiply by the, what is it that you call, I forgot the name for it. I know it's the transpose in the complex conjugate in English, in complex numbers, but I forgot what it is called in the case of the radicals. Let me tell you what I'm talking about. Let me stop sharing the screen. Share with you another screen, this one. Let me tell you how the algebra works, okay? Where is my pen? Here. Okay. So basically, when you have a radical expression, like the form, for example, a plus square root of b, okay, and you invert it, you're supposed to look for 1 over plus square root of b. So what you do in this situation, you multiply as if you're doing complex numbers. I forgot what it is called. Okay, so this is how it's going to end up being, basically a minus square root of b. You multiply both terms by this difference in here. This denominator will be a squared minus b squared, minus b, I'm sorry. And the numerator will be a square root of minus b square root of b. You guys understand what I'm saying in here or not? You multiply by this, you know, because remember, gamma plus itself will have that R over 2L, which is just basically the big gamma, plus the square root of things in there, which is in this case lambda. But you don't have to, plus the square root of r over 2l squared minus 1 over LC. Okay, that is gamma plus. So if you want to find tau plus will be 1 over basically r over 2l plus the square root of r over 2l squared minus 1 over LC. So again, following that idea, we multiply both terms by r over 2l minus square root of r over 2l squared minus 1 over LC, and divide by the same term, r over 2l minus the square root of r over 2l squared minus 1 over LC. Okay, if we do that, in the denominator I will have this term squared minus just this argument in here, and the minus will be positive, so the answer should be, so I'm doing it for you guys for tau plus. Hopefully you guys can do it for tau minus. So the denominator will be r over 2l squared minus r over 2l squared minus 1 over LC, basically this term, okay, or this term if you wish, it's the same thing, without the square root. And the numerator will be simply r over 2l minus square root of r over 2l squared minus 1 over LC. Okay, this term and this term cancel, and the minus becomes positive. So at the end, what we will have is 1 over LC, and in here I have r over 2l. Minus square root of r over 2l squared minus 1 over LC. Okay, 1 over LC is going to be just LC times that stuff, so it's going to be r times c over 2 minus the square root of, again I'm going to square that number, so it's going to be 1 over LC, so it's going to be LC squared, so it's going to be r over 2l times LC squared minus LC squared divided by LC. This is tau RC over 2. This is L squared, cancels one of these L's. What is it that we're supposed to show in here? So this will be LC, okay? And LC is just a product of the two. And I'm trying to think in here because, yeah, I mean, the L squared cancels the other L, and I will be left with, what is the expression that we're supposed to show? Yes, okay. So let's see here how that works in the end. For some reason, I'm getting a oh, this is squared. I'm sorry. This is squared. That's what the problem was. When you're doing things live like this one, sometimes you get okay. So the L squared and the L squared cancel, and the R times C, both of them squared. So that's all too good. So it looks good. So this is tau RC over 2 minus square root of R times C squared, which is tau RC, divided by 2 times 2, which is 2, squared, minus, again, I will be left with an L times C, and an L times C is, of course, R over, I'm sorry, it's an L over R times RC. And this is what we have defined at tau RL, and this is tau RC. So this is actually tau RL times tau RC. So this is the proof for it. Okay, did you guys follow the proof? So all you did was invert it, okay, and you multiply by the expression. I'm afraid to say that it's the conjugate, okay, the rational conjugate, I guess, because that's how it's called for complex numbers. Complex conjugate. Yes, no? Only algebra. Okay, Daniel at least is good with it. So hopefully everybody else, if not, please ask the questions, okay? So, no, we're supposed to continue the instructions. So I did just the tau plus, okay? You need to do the tau minus, and it's going to be the same thing. Except that, I think I have a problem in here. This should be a minus, and this should be a plus. You need to fix that. I think the signs in here are... So please fix the signs, okay? We just showed it. It's a minus, actually, in here. And this should be a plus. So at the end, you're supposed to do this, and it should not be hard to do. The point in here is I'm expressing the time characteristic for the positive solution and the negative solution in terms of that time characteristic for the RC circuit and the RL circuit. And we did the RC circuit already a long time ago, and today's turn is for the RL circuit. Okay. Again, Q is the sum of the two. Instead of working with the tau, it's actually much better to work with the gammas. Okay. Okay, when the initial conditions are t equal to obtain an expression for B plus and B minus. The general solution then is the sum of the two solutions because we found two different gammas, okay? So the general solution is the steady state. Here is your steady state. Oh man. What is this? Cancel. So that is the steady state. It's not allowing me to write the A in there. Every time I try to write the A, it's giving me something else. Steady state. And this is a transient, actually. As you can see, the transients, they should be always decaying. I know you're saying gamma can be an imaginary number, so therefore it can be not necessarily oscillating. I mean, it can be oscillating, not necessarily decaying, but it has a real part, and that real part will always ensure that it decays, even with oscillations. Okay, so this is the transient. Both of them, with the B plus and the B minus, are transients, and the C plus, this part in here is going to remain no matter what. Okay, again, you're supposed to take this expression and put t equal to 0, which will give you C epsilon plus B minus is equal to Q naught. So that's equation 1. Equation 2, take the derivative of this expression where you drop a minus gamma plus in here times B plus, and you drop a minus gamma minus times B minus, and you're going to equate this one also to I naught initially, and you solve two algebraic equations for B plus and B minus, knowing Q naught and I naught. Does this make sense to you guys? So you have the expression for Q. You take its derivative. Now you have the expression for I. You impose the condition at t equal to 0. Q is equal to Q naught. And I is equal to I naught. And from there, you solve for B plus and B minus in terms of Q naught and I naught. Good? Does everybody understand what's at stake in here? It's going to be a little bit of a long algebra, but it's just two variables with two equations. It's a 2x2 matrix if you did linear algebra. If not, just by substitution or whatever method that you have to find the B plus and B minus. This should be actually high school stuff. Does it make sense to you guys? Yes or no? If it doesn't make sense, I mean, I couldn't really say it's high school stuff because of so many symbols left and right in here. It makes it so hard to basically keep track of. But it should not be hard in terms of, at least in principle. because of the fact that I will have two equations with two unknowns. Yes or no? Okay. This one person is thinking that. Okay, very good. We have more than one. Very good. So, question 5. Using the diagram that the same stuff, construct a circuit, not end the circuit, okay? RLC circuit, basically, with a DC voltage of 12 volt, RL, R resistor, which is 10 ohms, the inductance, bring it down to 10 Henry, don't leave it at 50, and the capacitance, leave it as 0.05 Faraday. How long does it take your circuit to reach its steady state? Remember, the steady state is that C times epsilon. So basically, when C is equal to what? C is equal to, in this case, is equal to 0.05, and epsilon is 12. So multiply 12 by 0.05, the answer should be 12 times 0.05, 0.6 coulombs, okay? 0.6 coulombs. So look at the charge across the capacitance in here. So when you build your, I'm leaving it up to you guys to do it, because this is really something that I'm hoping that you can design your circuit similar to what we did earlier, except now you have a capacitor also. Let me show you quickly where that is, okay? Stop sharing the screen and share with you the circuit itself. So it's going to be similar to this, except you're going to add this capacitance, okay? And you change this one to whatever it tells you, is it 10 Henry? And the capacitance, once you plug it in, you bring it to the smallest value, which is 0.05. If you're going to use this circuit, I would recommend you close this one and open it again, okay? Because sometimes there's values that remains in here. Like, for example, there is already a voltage across this one in here, so that's going to mess up your initial conditions, okay? So close this completely and open a new one and add stuff as you need, and make sure the voltage in here, it says 12 volts, okay? And this one, change the value of it. You can just right click and change inductance to the value that is needed, 10, which is the lowest value in this case, okay? And change the resistance to leave it, I mean, it comes at 10. But the capacitor, I mean, when you add it, make sure change the value to the lowest value possible, which is 0.05 farads, okay? So now, you're going to build this circuit, basically. But when you do that, try to bring this one to the ends in here. Don't connect it to the resistor, okay? For some reason, I have a voltage already across it, okay? Make sure when you bring it in there, then the voltage should be Q over C. And Q at the end, so the voltage at the end should be 12 volts, because C is 0.05, and then times the EMF, which is 12, and you divide it by C, 0.05, so the voltage at the end is 12 volt. So put it in across the capacitor and wait to see. Basically, you start the animation. You start, first of all, the timer while you're paused, and then you start the animation. I mean, you start, first of all, the stopwatch, and then you start the animation and wait for the voltage to reach 12 volt. Obviously, it's not going to reach it because of internal resistances and things like that, but it's going to reach saturation nonetheless, okay? It's going to change no more. At that point, you're going to pause it, and you're going to tell me how long it took for it to reach that saturation, okay? And let me stop sharing the screen and go back to the questions. Okay, how long does it take your circuit to reach its steady state? That is basically the value that we're looking for. How did you design your circuit to include a picture of your circuit? So we're going to take a picture of it and what you did and explain what you did in here. Does everybody understand this question? Okay, at least one person is. I'm assuming the others, since you're not objecting, you're fine with it too. Or maybe you turned on your computer and you left. Okay, at least Sebastian is still in here. Okay, good. So more than one. So now we are talking about the Lrc resonance, which we did not do really in lecture yet, but we're going to do it on Wednesday. Okay. So again, as I said before, the lab is really not due this week, so we still have time to work on it. But the point being in here is that you really need to get this stuff together to get it going. So basically in RLC circuit, you have now, again, a resistor, capacitor, and inductance, but the power source now is not steady. All of these power sources up to this point were constant voltage, were a regular battery. This one is the one that you plug in the wall, okay? Or if we're doing it in the lab, there is actually power sources that alternate, okay, that you can control the frequency of the signal, control omega basically, okay? So again, it's similar to the previous one, except now instead of having the epsilon on the other side, I have V naught cosine omega t, okay? We define something called the reactance, and the reactance is omega times L for the inductance, and the capacitance, we define it to be 1 over omega c, okay, for the capacitive reactance. Reactance is similar to the resistance, okay? It has the same units as the resistance. The unit for XL is omega. The unit for XC is omega. The unit for the R is omega, which is actually ohms, I should say, okay? So this is in ohms, this is in ohms, and the R also in ohms. So all of them are in ohms. And the impedance, which is defined in this fashion, also is in ohms. All of them in ohms. All of them, they are similar to a resistance in terms of units, and they behave like resistance, okay? Like R in a circuit. As long as you have an alternating current source, this is how the inductor, if you wish, reactance, which is the resistance, the equivalent of a resistance, is. This is the reactance, which is the equivalent of a resistance for a capacitor is. This is for the entire circuit how it is, okay? And there is a phase shift. Remember, the signal is coming with no phase. It's coming at cosine omega t. At t equal to 0, this starts to oscillate right away. So it starts from a maximum value and starts oscillating, okay? This is the signal. But the current itself in the circuit and the other voltages may or may not be in the same phase. As a matter of fact, the current in the circuit is shifted by this amount. So in other words, can I change colors in here? I don't know how to do that. So basically the current may be at a different angle in here. Oh man. Escape. So it may be, no, it should oscillate with the same omega, so I can't do that. Maybe it's like this. There is a delay between the peaks, for example, and that delay is exactly this phi. It's exactly this phi, the difference in the two, okay? So there is a phase shift, and this is the phase shift and how much it is. It depends on how much the difference between the reactance of the inductor and the reactance of the capacitance, and how these two differences are. So if they're the same value, if we have the same value, then in this case it's 0. There is no phase shift. Okay. Now, if the circuit has a lot of inductance in here versus capacitance, then the shift is positive. Okay. If the capacitor wins, in this case, the shift is negative. The current actually lags behind the voltage, okay? And in the first case, it's actually ahead of the voltage. So in other words, like in this case, it's lagging, and in another case, it's going to be ahead of it. So it's going to reach its maximum before the other one does, okay? So that's what that positive and negative shift is. In other words, I don't have a cosine omega t in here. I have a cosine omega t plus phi. This phi has several positions, either 0, when I don't really have a phase difference between them. They are in the same phase. They are in sync, okay? They hit the maxima together and the minima together, and they cancel, they vanish on the same time. Or there is a lag, okay? One of them is reaching its maximum before the other one, okay? And which one lags depends on this sign. Which one is ahead depends on the sign between on phi. If phi is positive, actually in this case, the current will be ahead than the voltage. Okay, the current is exactly where the resistance is. In other words, the voltage across the resistance is going to be ahead. When it's the opposite situation, the voltage actually, the current is lagging behind. Okay, so it pulls on it and it's like behind it. So that's basically what the expression is. Did I put a plus sign? It's actually a minus sign. Okay, this is how the expression looked like then. Okay, Q of t, I sub t, and this is the voltage that caused the whole thing. Again, we're focusing only on the steady state. There is a transient also that decays exponentially in this case too. So when you turn on the switch, there is that big jump up and down, but then it's immediately canceled because of the high resistance, okay? And then the system starts to oscillate. So we're neglecting the transient again, just as we did it earlier in there when we were talking about the transient. So transient is actually a problem, but in this situation, the response, which is Q now, is going to be proportional to V naught. And the V naught is the intensity of the excitation, the intensity of the current, actually. That's called the intensity of the voltage. So there is actually a missing part to the solution if we really are trying to be picky about it. There is the transient if I'm talking about the whole solution. This is not the complete solution. This is just the steady state. Okay. The current also, which is a steady state current also, is this one. All you have to do is take the derivative of this expression with respect to t. The omega cancels the omega, and this is basically what happened in here. I'm sorry, so this is a z. Okay. Can you guys fix this quickly? On page 8. Okay. Page 8, fix current. It's clear when you take the derivative, the omega cancels, okay? And the z stays in the denominator. So that's a typo when you're too busy trying to get things done. And sometimes you get excited. Because a lot of this, even in Word, they use LaTeX, and sometimes they're for not to paying too close attention to what I'm writing. Sorry. So hopefully you guys caught it. And you're supposed to be in calc-based class, so you should be able to fix this on your own. Again, it's fixed in here. So this is the voltage across a capacitor, which is just the charge divided by C. The charge is here, okay? And this is 1 over C. Omega C is actually excess C divided by Z. The voltage across the resistor is this current fixed, of course, divided by Z times R. So it's fixed in here. It's fine. It's working beautiful. And the V across the resistor is actually the derivative of this expression twice. So the derivative of the cos is a negative sign. Here it is. And the omega will come again. And the omega will drop one more time. And when you multiply it by L, that is actually XL. So XL divided by Z times V naught. So that's exactly, all of this are the steady state. They are not the transients. There is transients. There are stuff that is in there. But we're assuming we waited long enough so that the transient has no effect on the solution. We're just focusing on the steady state. This is typically what you do. What caused the bridge in Tacoma, and I know that you have a picture of it in your book in Physics 4A, to collapse was due to a similar phenomenon, because when they built the bridge, was they had the natural frequency, which is 1 over square root of LC in this situation, or square root of K over M in that case in the bridge, was very close from the oscillation, from the wind frequency, and the bridge reached resonance, so it was oscillating with the utmost amplitude because of the wind, and basically collapsed. I don't know if you guys have that, and if you remember that discussion that you guys have had in Physics 4A. Did you guys remember it? I don't know who. Some of you probably have different professors. I did not have none of you guys. But if I did, I would have made a big fuss over it there then. Did you guys have any discussion along this lines for the Tacoma Bridge? You did for us? Good. Anybody else? Okay, it's an interesting discussion because engineers messed up that time big time. That place big time. The resonance can be sometimes an undesirable effect, and sometimes can be something that you want. Actually, for example, for any kind of signal, for example, telecommunications, you would want resonance. You would want the signal to be amplified. Okay, so it's really not always something bad, okay? But in the case of the bridge, it was a big disaster. You don't want to build a building and then have its natural frequency very close from whatever next earthquake. So the slightest thing is going to collapse on its own. Don't want that. You want high damping enough so it cancels. Yeah, okay, right. Yeah, the glass is fine, but not the whole building. Glass probably can scratch you or can maybe do something. As long as it doesn't fall right away, especially those big windows, they're too heavy of a glass. Anyway, show algebraically that this VL and this VR and this VC from this expression, they add up to V naught cosine omega t. So you add them up, and they will give you exactly V naught cosine omega t. Note the following. Cosine of the difference of the angles is cos cos plus sin sin. This is trig identity. A sin of the difference is equal to sin cos minus cos sin. Those are two trig identities. Also, you need phi because somehow you need the cosine of phi and a sine of phi. Because phi was given by this expression, its cosine and sine can be expressed in terms of the tangent. The tangent of phi now is just xl minus xc over r. So you can express those in terms of the tangent, and they turn out to be the cos of phi is just r over z, and the sin of sub phi is going to be xl minus xc over z, where z is this square root. Okay, so I have everything. You have everything in these expressions. VL is V naught minus V naught times XL over Z times sin of the difference, and I sub the sin of the difference from this expression, and once I reach cosine of phi, I replace it by R over Z. Once I reach the sine of phi, I replace it by this expression. So we're in business. Now plus VR. VR is V naught R over Z cos of the difference. Cos of the difference is given by cos cos, and now I need that R over Z, plus sin times sin, and I need that expression for the sin. And I'm in business. The last term I need is VC, and VC is V naught XC over Z times sin of the difference. Sin of the difference is exactly here. Okay? Sin cos, so I need that cos again, minus cos sin, and I need that sin again. And it's a long expression, but it's doable, and at the end, everything cancels. The only thing that is going to be left on the other side is V naught cos omega t. So you have checked, actually, that this is a solution with all of this stuff in it to this equation. Does this question make sense to you guys, at least conceptually? I know there's a lot of work in it, but I'm hoping that you guys can do that. Remember, this lab has implications on your exam too. So this is, think about it as a review for the exam. If you guys are going to major in any kind of electronics or electricity, you will have a lot of these things. You have far more complicated situations, and you will not be using trig functions, though, I must tell you that. And we're going to devise a way of doing it actually in this lab too. And on Wednesday when we meet, we're going to use the Phasors method, which is a little bit easier, geometrical method. Or if you wish, we can use complex numbers. And complex numbers makes life a little bit easier. Complex numbers take complex problems and make them simpler. So one of the two methods we're going to use to solve this kind of complicated algebra. But for right now, deal with the cos and sin everywhere. You don't have to cos and sin, though. Do you guys understand this question or not? Do you guys know what you're doing for this question or not? Yes? Okay, at least I have one person in here. Two, good. So I think we're in good shape now. Man, we are just in question 6. We still have so many questions to do. Okay, so the oscilloscope data. Okay, you're given values for omega. You're given values for you have values for R. This is not the same data, by the way, before. Okay, this is different stuff. So you're given L 10 millihenry, which is more practical actually what you do in the actual lab. Okay, the first simulations are just simulations. R of 5 ohm, capacitor of 100 microfarads. Now we're dealing with real numbers, okay, microfarads and things like that. And the voltage is 10 volt. We will allow omega to remain as independent variable. Now, if omega is 500, use the previous expressions for XL. Remember, XL is omega times L. Omega is 500 radians per second, and L is 10. So you multiply the two, and you find how many ohms is that. And you do the same thing, XE, which is 1 over 500 times this capacitance, and you tell me how many ohms is that. You find Z, which is the square root of 5 squared plus the difference between the XL minus XC squared. Again, you have everything in here. You have phi, which is the arctangent of this XL minus XC divided by 5. Okay? And you have VR, which is simply equal to V naught times, V naught. First of all, you need I, okay, in order to find VR. VI is equal to V naught divided by Z. Okay, I did not write it down in here anywhere, I guess. So you need I first, okay, to find VR. Oh, I'm sorry, we have the VR here. Okay, VR is V naught R divided by Z. Okay, you have V naught, you have R, you have Z. You have just calculated everything in here, so you should be fine, and you should be in good business. You should be in great shape in here. So you can find VR, and you can find VL again, and you can find VC. Here they are. VC is V naught XC over Z. VR is V naught R over Z. And VL is V naught XL over Z. Do not write the minus and do not write the trig functions, just the absolute values, okay? The maximum amplitudes, okay? Here is the question before that, okay? Usually, I mean, here is actually question 5. It gives you those answers. We don't usually write the phase. We don't even write the signs. Those are assumed, okay? Often we will ignore the time dependence of the component voltages and assume that they are implicitly included and write simply. So instead of writing these expressions that I was referring to earlier in the calculations, we don't write this. We write them like this. We just get the amplitude, basically the coefficients of the cosines and sines. So when you sub in here, use equation 5 for the part VC, VR, and VL. For XL, XC, and Z, they are in the previous page. Here is XL, here is XC, here is Z, and phi is given by that expression. So you have everything. Does this question make sense to you guys? Question 7. It's simple substitution. But don't forget the units. For XL and XC and R and Z, they are all in ohms. And the VR and the VC and the VL, they are all in volts. And the phi is an angle. So probably the calculator is going to give it to you in radians. Make sure it's in degrees, or you can make sure it's in radians too. It's fine. It's usually good to express it in degrees to have an idea, because we can, I mean, number of 1.23, I don't know, understand it very much compared to a number of 67 degrees, for example. Do you guys understand what this question 7 is? Yes or no? Or maybe. Okay, Faraz and Sebastian. Good. So, and Daniel and everybody now on board. Question 8. Now, for this question and the rest, you're given this data actually. This is given to you as if you're doing it in live. So what we did in here, I gave you data. Okay, so these divisions are 5 milliseconds per division, but this one is 5 milliseconds. Okay, this is with it 10 milliseconds and so on and so forth. This one is 20 volts. Sorry, what did I say? This is 5 milliseconds. This is a millisecond. This is 1 millisecond, 1 millisecond, 1 millisecond, 1 millisecond, and this whole thing is 5 milliseconds, okay? The same thing in here. This is 20 volts. Okay, this is another 20 volts and so on and so forth, okay? And these are voltages. So you're going to go from peak to here and find how many volts that is. You're going to go from maximum to maximum, for example, and find the periods in here. So that's basically what the question is. 0 to peak and all of that to find the amplitude and so on and so forth, okay? To measure the period, count the number of divisions for a complete wave and multiply it by the factor, which is 5 milliseconds per division. And what is the period t? So you're going to find how many divisions there are in here, how many this, or how many small ones in there. You can use a ruler for it if you wish, okay? Once you find t, remember omega is equal to, what is it? 2 pi over t, okay? Since t is equal to 2 pi over omega, then once you find the big period t, then you just can find what omega is, okay? And then you need to compare it to 500 radians per second. Did you find it or not? It should be close from it. Then you're going to measure the peak for the power supply. Here is the power supply. This is the power supply. This peak is it about 10 volts, okay? So where is the power supply? Yeah, remember this whole thing from here to here is 20 volts, okay? So you're supposed to have about 10 volts in here. And measure the 0 to peak amplitude for the capacitor, resistance, and inductor and put them in the table. So basically do the same thing. This is the capacitor, 0 to peak in here. It's probably more than 10 volts in here. And this one is probably less than 10 volts, and this one is probably less than 10 volts. So this is the inductor, the resistor, the capacitor. Okay? And report the data here. First of all, I'm sorry, you should have reported from question 7 all of these answers in here. Okay? And in here, you're going to report the questions for the voltages in here from these questions, because this question will ask you for the voltages. Where is the question for the voltages? 0 to put amplitude. So we're going to report that in here. For the XL, how much voltage in here? For the XC, how much voltage in here? And for the Z, how much voltage in here? Okay? So again, it can be shown that equations 2, that XL, no, this is not equation 2. This is a different. You have XL equals to this, XC equals to this, using your measured values from 5, not from 5, from this step. This is again, this one from 10, question 10, okay, from the previous question. And R equals to 5 ohm, calculate XL, XC, and Z. So basically, I want you to compare the data. I want you to compare what you measure versus what you calculate. The phase phi refers to the difference in supply and the voltage, since the current is equal to the phase angle is easily measured. So in this case, you're going to between the current I, since the current I can be is measured, the phase angle is. So you have the resistor. Here is the resistor to find the phase, and you have the power supply. See where the peak is, and see where the peak is for the other one, and or the peak in here. Okay, the peak has to be very, very immediate. Is it first of all negative? Is it lagging or is it ahead? Because the voltage across the resistor is proportional to the current. So this is actually the current too. All you have to do is just divide it by R. The voltage over R divided by basically R will give you the current itself. So what we're measuring this phase difference. So that's where phi is. So this is what phi is. And it's going to be a negative number in this case. At least that's how it looks to me, unless you guys disagree with me. So the voltage is actually ahead of the current, or the current is lagging behind the voltage. And you need to find this difference That is delta t. That's the difference in time. Okay? You have to multiply it by omega to find it in radians. So omega delta t is actually going to be the difference in phase. That's going to be phi in radians. If you want to multiply it by 180 divided by pi to find it actually in degrees. So you can find phi from this measurement. Do you guys understand it? How to find phi? Find a peak or any point that you specifically can look for. When they vanish, for example, both of them. Who vanishes first, and then how long does it take for the second to vanish? Now you found the time. You didn't find actually an angle. You found the delay in time. You have to multiply it by omega because omega times time is actually the angle, but it's going to be in radians. You can convert it to degrees by multiplying it by 180 and divided by pi, and now you know how much phase difference there is. And which one is ahead, basically? Is it the voltage or the current? Of course, you're not given the current data in here, and that's why the warning was saying you really don't have the current, you have the voltage across the resistor. But because the voltage across the resistor is proportional to the current, because remember Ohm's law says V equals to Ri, then in this case you really have also the current. Do you guys understand this question? Yes or no? Or maybe? We're supposed to find the phase now. At least one person, two. Good. So basically, I'm hoping that you guys can read the instructions and you should be fine, okay? So in this case, we're going to find the phase difference in here and compare the two, because you can calculate it also with a calculator using arctangent of XL minus XC divided by R. And again, that's going to be in radians. If you put it directly in a calculator, you compare the two radians, or you can put it in degrees and compare the 2 degrees and see if it makes sense to you. Okay. Okay, here is actually the instructions. I'm sorry, how to do that. Okay. To measure the phase, proceed as follows. Measure the time difference, delta t, between the zero crossing. You can do the zero crossing of the maxima, okay, and the zero crossing for the other one. At the same phase, multiply delta by 360 divided by the period. That's another way of doing it, okay? Okay, which you measured in question T, you enter. So remember, I multiplied by omega with 360 is just 2 pi. Okay, so that's basically the equivalent. Enter your value and calculate the error. So basically, you could do that too. So now you have okay, I'm sorry, I may have referred to something else earlier when I was. So you measured XL in theory from question 7, and you measured XL from the voltage again, okay, from the previous question, and you have the voltages in here. This is the Phasors method. Man, we're 4 o'clock already. Started at 2:30, so it's been more than an hour and a half now. But let's finish this quickly. In the Phasors diagram, we write the voltage across the resistor on the x-axis. Because it's a sine function, the XL has a minus. If you guys cosine saw that with the trying to find the page, minus, and you have a minus in here, so it's actually shifted upward by 90 degrees actually, and I can show, we can see why that is. Okay, it's the same basically phase. Okay, here is it. So the voltage across the resistor is a cosine, correct? The voltage across the inductor in this case is going to be minus sine. So what a minus sine is, let me stop sharing this screen in here and share with you this screen. Let me make this case in here. So across the inductor, ignore the value, ignore the amplitude. We just focus on the cosine and the sine only for right now. So across the resistor, it's cosine of something. Okay, it's cosine of something. Across the inductor, it's a minus sine of the same thing, times the arguments which are slightly different. there is cosine, let's argue this case in here, a cosine of the same thing, which was omega t if you wish minus phi. This is omega t minus phi. Okay, so I'm going to write it down if you like. It's the same thing, which is omega t minus phi, plus pi over 2. Okay, if I do this and apply the trig identities before, cos of the sum of the two angles, cos, so it's going to be cos of omega t minus phi times cos of pi over 2 minus sine of omega t plus phi, sine of pi over 2. This is 0. This is 1. So in other words, this minus sine, because I have a minus in here, is the same thing as a cosine, but shifted with a positive pi over 2. So the voltage across the inductor is actually ahead of the resistor by 90 degrees. The same argument holds true for the capacitor. The capacitor VC is the same thing, except it's a positive sign of the same positive sign of the same thing, which was omega t minus phi. So following this argument in here, I can do the same thing in here. I can say, it looks to me like this looks like cosine of the same stuff, which is minus phi, minus pi over 2. Let's look at this expression. Well, using the trig identity, this is cos, and cos is going to be 0 because of cos of pi over 2. So this is cos of the same stuff, omega t minus phi, okay, times cos of pi over 2. Again, this is 0, so this whole thing is 0. Minus, the trig identity will give me a plus, so cos becomes the sin of omega t minus phi times the sine of pi over 2. Well, this is 1. So the sine with a positive sign is the same thing as if it's a cos, except with a negative angle. Okay, so the voltage across the inductor, the capacitor, I'm sorry, is lagging behind that of the resistor. The voltage across the inductor is ahead by 90 degrees. So that is taking advantage of this stuff. We're going to draw this thing this way, using what is called the phasors. So ignore the omega t minus phi and make them minus phi and make them equal to 0. So since I have in here the voltage across the resistor, then is going to be with the x-axis. The voltage across the inductor is going to be ahead by 90 degrees. The voltage across the capacitor is going to lag by 90 degrees. And then depending on the difference between them, if the difference is exactly 0, then the z, which is just going to be along the r, is going to be exactly equal to r at that point if they cancel one another. If not, I'm just adding vectors basically. Add these two vectors, this one, subtract from this one, this is the difference between them. Now I have to add this vector to that vector, and that is really what this impedance is. So the impedance now is, in this case, z equal to the square root of, using the Pythagorean theorem, of r squared, which is this side, plus the difference between XL and XC squared, and the whole under square root using the Pythagorean theorem. So this is in a nutshell what phasors are. Okay, this is the method. So that's exactly what the point in here is. So the XL is ahead by 90 degrees at 12 ohms. So you're going to replace the values and use the identities to find all of these answers. So we're going to get more in it on Wednesday when we meet for the class, okay? So in the space, don't forget that I promised to do problem 59 from chapter 30 first, okay? So which we need to do. So in the space provided, draw your phasors. So they give you these numbers now. So you're going to have R equals to 5 ohms. So we're going to draw 5 ohms in here, 5 by itself. You're going to find C is given to you 100 microfarads, and omega is 500 radians per second, and L is 10 millihenry. You multiply 10 millihenry by 500, and you're going to find how much it is on the y-axis in the positive direction. And you're going to take 1 over 100 microfarads times 500 radians per second, and you're going to find how much XC is. And you're going to find the difference between them somewhere in here or somewhere in here, depending if the circuit, if the inductance is winning or the capacitance is winning. And if they are canceling one another, they are canceling one another. Okay, neither is winning. And then you're going to take the resultant. If this turned out to be there, you're going to draw it in such a way that the resultant is in there. That is Z, actually. That is the total impedance. And or it's going to be in the bottom, depending, again, if XC is more than XL, it's going to be in the bottom. Okay, and if they're not, if they're equal, then it's going to be exactly equal to R. That's easy. If they're equal, then Z is going to be exactly R. Okay, because they cancel. Remember, the square root of XL minus XC is going to be 0. And that part plus R squared, so it's going to square root of R squared, which is just R. Okay. Then you change the frequency. Then you're going to tell me, depending, actually, this question will, what is it, 15, 14, will depend exactly on this graph. If it is above the x-axis, then it's inductive. If it's below the y-axis, then it's capacitive. If it's neither, basically they cancel, it's neither. So that's question 14. Then you're given this data now. You have omega is changing from 100 all the way to 10,000 radians per second. VC is given 10.1 volts and 20 volts, and then comes down. VR is given 0.5 and then increases 10 volts and then comes down. VL is given across the inductor, also is given, and then it reaches some value and comes down. And the phi is a negative number, then it cancels, and then it becomes positive. So this data is given to you instead of actually doing it in the lab, because we're not together to collect this data. I'm providing you the data, okay? So you have it for different frequencies. So we're changing frequency in here and getting this data in here, okay? So this is not the previous data. Do not rely on the previous. In other words, L and R and all of that is not necessarily the same as before. So this is different things in here, different RLC circuit. So we're going to make a semi-log plots of the above data. Namely, we're going to log of these expressions in here. Because remember, from 100 to 10,000, if I'm going to draw it, it's going to be a very long paper, okay? If you put it in Excel, doesn't make sense. So I'm going to take the log of this expression and write the voltages as a function of the log, okay? And you're going to plot them in here. VC, VR, VL, and phi also. So you have the data in there. Okay. So in here, all you have to do is just you did, okay? Because I need that data in there, okay? And then for what value omega, VC, VR, and VL have a maxima. Just look at your graphs or look at your the data. You should find when these things are maximum. For what value of omega they make it, okay? This value is called the resonant frequency, and what is the circuit is said to be resonant. Compare the value to omega. Oh, I'm sorry. You still have to use the same previous values because you need to compare that resonance frequency with the values that were given to you from before, okay? Namely, L is equal to 10 millihenry, R is equal to 5, and C equals to 100 microfarads. But omega is changing now. It's not fixed, okay? So there is a value of omega that makes these things maximum. So you're going to look at your data, and you should be able to find it. That's not hard. And you're going to compare that value that makes this voltages their best with this expression in here. Okay, for the natural frequency. It's not going to be exactly equal, by the way, but it should not be too far from it. What is the value of Z at resonance? So again, the value of Z at resonance should be maybe have to do with the R, because at resonance, these two should be canceled. The circuit is not inductive or capacitive. They should be really, typically this is the value, so it should not be too far from 5 ohms. Again, you have VC, you have VR, you have VL, so you should be able to get all of that expression, okay? for what value? Okay, and what is the value of phi at resonance? You can look at this data and you should be able to find it. Okay, at resonance, remember the value from phi changes from negative 87 degrees all the way to positive 87 degrees. So somewhere where it's at resonance, which is typically in the middle, that is where the phase is. So there should not be any phase at that point. Because again, XL minus XC equal to 0. So arctangent of 0 is going to be 0. Okay. Show algebraically from equations 4 and 5 that resonance frequency. So basically now you're going to go to the algebra and do the stuff I was telling you, okay? That Z is equal to R, VL and VC are equal to one another, and they're equal to this quantity, and VR is equal to V naught. So that's basically how much things in here. So VR should be V naught, and the other two voltages should be the same. Okay. For very low frequencies, when omega is very, very less than 1 over C, the circuit is more capacitive, showed algebraically. So now we do the algebra. When basically omega is very low, in this case, 1 over omega C will dominate. In other words, XC will dominate, and XL will go to 0. So in the expression that we've been dealing with, let me show quickly in this one in here. I promise hopefully to finish this one in less than 2 hours. It looks like we're headed to 2 hours. So let me stop sharing this thing in here. So remember, for example, for Z is equal to the square root of R squared plus XL minus XC squared, okay? Oh man, I'm not sharing my screen. Sorry. So this is the value of Z. Remember, XL was omega L, and XC is 1 over omega C. When omega is very, very small compared to 1 over square root of LC, very small, this value in here will be much bigger than this value, because here you're multiplying by a small number and here you're dividing by a big number. So XC will be much, much bigger than XL. All you have to do in here is just basically, if you want to, square this expression. That means omega squared is much, much less than 1 over LC. Okay. Multiply by L, so you'll have an omega squared L much, much less than 1 over C. And divide by one of the omegas, so you'll be left with an omega L much, much less than 1 over omega C. In other words, XC will be very big compared to XL. Okay. Since that's the case, this expression now will dominate. So this will go to 0. And Z itself will be the square root of R squared plus XC squared. Okay. And the phase then phi will be equal to arc10 of XL minus, which is always XL minus XC, divided by R. But remember, this one is negligible in front of this one. So at low frequencies, this is the phase. It's negative. As you can clearly see from the data, it was negative. Here it is, negative for low frequencies. And it should be very close from negative infinity, negative 90 actually. And for high frequencies, it's omega L that dominates 1 over omega C, because you're going to be dividing by a big number. So omega XC will be 0 versus XL, which is going to be high. So in this case, for high frequencies, XL will dominate, so XC will be negligible. XL minus XC is going to be positive, and the phase will be positive. Okay? So that is basically, in a nutshell, what these things are. So we're going to do this for both very low frequencies and high frequencies, and you're going to write your conclusion. Good? This is your lab. It's worth 132 points, I believe. It's 2 labs in one. So don't forget the discussion for the whole day is about this transient business and the fact that we usually don't deal with it because we focus more on the steady state. And you're going to give me examples of that from what you think you can find. You can Google stuff if you can find it, I mean, in your day-to-day things. Is everybody good in here, up to here? Okay, I'm going to stop the recording.